So in this video, we'll have prerequisites to prove the fundamental theorem on finite abelian groups. First, we have this problem in which we have to prove that G is the internal direct product of n1 etc. nn if and only if the first condition is G is the product of n1, n2 and so on nn, and the second condition is ni intersection this product without this ni is singleton E where the ni's are normal subgroups of G. Now to prove the first one, that is assuming that G is the internal direct product, we make use of the definition and then prove the two conditions. So in this definition we have the first condition to be G is the product of n1 etc. nn. So that is what we have here. So it is enough we prove the second one alone. So for which you consider x to be in the intersection. So when x is in the intersection, you have x in ni as well as x in the product also. So in this product you don't have this ni. So x is in ni means x can be uniquely written. That is the second condition. So using that you have this step, and because x is in this, again by the same condition you have x being written in this way. So again by uniqueness you can equate this with this and this with this and so on. So x with ei, because in the ith place that you have this, so x is equal to ei. But you don't have different ei's in ni's which are normal subgroups of G. So you have that e being the identity element in G, we have that ei equals e. So you have the intersection consisting of only one element, namely e. Now for the converse part, we shall have the first and second conditions to be true. To prove that G is the internal direct product of n1 etc. nn, it is enough to prove the uniqueness, because the first condition is same as the first condition mentioned here. So you take an x in G with x being written as x1 etc. xn, and x is also written as y1, y2 and so on yn. Then we have LHS being equal, you have this step. Now these xi's and yi's are in the corresponding ni's. So from which we have this yn xn inverse being written in this way. Now to understand this, we shall just consider with the three elements what happens. With two elements it's very simple. With three elements, let us understand what happens here, so that the general case can easily be followed. Let us consider x1, x2, x3 to be equal to y1, y2, y3. Then retaining this x3, you multiply both sides by post multiply by y3 inverse, so you have this, and this one you pre-multiply by x1 x2 inverse. So this is what we get. Then this is nothing but x2 inverse x1 inverse. This y1 y2 is retained as such, and here we consider see we have an element from n2 and an element from n1. But because n1, n2 are normal subgroups, you know that n1, n2 is same as n2, n1. So we can write this element as w1, w2, and w1 is a member of n1, w2 is a member of n2. So you have this, and now coming to this one we shall consider. Again this is in n2 and this is in n1, but n1, n2 is same as n2, n1. So you can rewrite this in this way. So now that if you consider the whole lot, this is a member of n1 and this is a member of n2. So LHS is in n3 and RHS is in n1, n2, the product. So we have x3, y3 inverse belonging to n3 intersection n1, n2. So by the second condition, that x3, y3 inverse can only be E, so that in turn gives x3 is equal to y3. Same concept is followed here for the general case. So we have this yn xn inverse to be an element in this as well as in this is obviously an element in nn. So it is in the intersection, and therefore that intersection being singleton E by the second condition, we have to have the whole lot to be in the intersection which is singleton E. So yn xn inverse equals E implies that xn equals yn for all n. So that proves the uniqueness. That is the second condition. So you will have G to be the internal direct product of n1 etc. nn. Now in the second problem, if G is a finite group and n1 etc. nn are normal in G with these two conditions, then we need to prove that G is the direct product of n1 etc. nn. So here again, to understand the general case, we shall consider three normal subgroups, say H, K, L. So we will try to establish this in this case. Actually we make use of the previous problem. So for that, if I'm able to give H intersection KL to be singleton E, then automatically my G will be the direct product of N1 etc. Nn. So we shall consider order of HKL, which is order of H into order of KL divided by order of H intersection KL. Now we are given that order of HKL. We are given that order of HKL to be order of H, order of K, order of L. So you have this, and this one again you apply that order of KL, you rewrite that as order of K, order of L divided by order of K intersection L. The rest are retained as such. So we will definitely have this to be some integer. So we shall just cross multiply. So we have some integer times your order of H intersection KL to be just 1, because we have order of H, order of K, order of KL here, and the same thing over here, they get cancelled giving 1. So this implies that order of H intersection KL to be 1, because this is integer, this is also an integer. Equals 1 means we must have this to be 1. So that in turn gives H intersection KL to be singleton E. And just because K and L are normal, KL will also be normal subgroup. So H intersection KL, this subgroup just consists of only identity element. So by the previous this one, we need to have our G to be the direct product of H, K, L. So that concept is extended to N subgroups, normal subgroups in G. So we have, so it is order of HK, which is equal to order of H, order of K divided by order of H intersection K. Using that, first we write like this, and then this is given as this. So you just replace, and again the same thing, we have this to be some positive integer. Further, when you expand this and write, this is what you get, some positive integer. These two being the same, we can cancel. So we are cross multiplying and we are left with this. So this must be 1. So, and from that we get this. So by the previous problem, we conclude that G is the direct product of N1 etc. in N. Now the third one, if G is finite abelian group, then G is the direct product of its p-Sylow subgroups. So to prove this, we make use of the previous problem. The second one we will use. So we shall consider order of G to be M by the fundamental theorem on arithmetic. You can write this as P1 power alpha 1, P2 power alpha 2, and so on, Pn power alpha n. Obviously, P1 power alpha 1 divides order of G, and if you raise again that plus 1, then in that case it will not divide order of G. So by the definition of p-Sylow subgroup, this implies that G has a P1 Sylow subgroup S1 of order P1 power alpha 1, in the same way with P2 and so on. So also order of G is order of S1 and so on, the product order of Sn. So which is nothing but your order of S1 etc. Sn. So since this product is contained in G, one is contained in the other and both of them are of the same order. So we have order of G to be equal to this. So both of them are of the same order and one is contained in other. So we have to have G to be the direct product of S1 etc. Sn, and hence by the problem, see, it is actually the product only we have. Direct product comes using the second problem. So we have G to be the direct product of its p-Sylow subgroups. So this is where we have order of G being written in this way, which is same as order of S1 etc. Sn. So that is the main thing to have this one, and by the previous problem we get the G to be the direct product of its Sylow subgroups. Now next one we have the definition of order of an element, which we are already familiar with, and the maximal order. So these two definitions, and corresponding to them we have two results. That is whenever A is an element of G of order M and there is some other integer n for which A power n is E means, then what is the relation between M and n? This is least positive integer, this is any other integer. So the relation is M should divide n. So that we simply call it as least must divide any other. So the definition of order of an element is the least positive integer such that A power n is identity element in G. And now we have the definition of maximal order. When do you say that A in G to be of maximal order? Say n. If there is another element B in G with order B power m equals the identity element, then m must be less than or equal to n. You have any other element B in G of order m means then m must be less than or equal to n. Here this is considered as order of B. Now, so this result that we will prove that least must divide any other, and this is another result that we will be proving. After proving that, we can make use of that in proving the fundamental theorem on finite abelian group. So to prove this, we need to have this result. This result says that if G is a finite abelian group, AB belong to G, and if order of A is m, order of B is n, then there exists an element x in G such that order of x is the LCM of m and n. LCM of m and n. So this result will be used in proving this result, and result 1 and 3, they will be used again in proving the fundamental theorem. So this in short we will call as order of any element divides maximal order of an element. Order of any element divides maximal order of an element. So actually when you compare these two, because these two are very important in establishing the proof of fundamental theorem on finite abelian group, just crudely remember in this way that if you have the same element A, and in the index you have m and n, you need to use this. Same element, index different, least must divide any other. This result must be used. And when you consider this one, you have maximal order n, and this is any other. So A and any other. A of maximal order, and this is any other element. So A and any other element means you will have to have this result, order of any element dividing maximal order of an element, and A is the same, index is different means then you have to make use of this. Now we will see the proof of these three results. So in the first result, this is what we have. We have A in G to be such that order of A is m, which means m is the least positive integer, for which A power m is the identity element. We shall consider A power n to be E. Now we shall apply Euclidean algorithm to n and m, so that you can have your n to be, you can find two more integers q and r with r lying between 0 and m. R can take the least value 0, or r should be less than m. This is Euclidean algorithm. But here what we claim is r must be 0. So suppose we have this one to be true with 0 less than r less than m. One condition, two conditions are there. We are going to say, we are going to rule out the other condition and state that only this condition is possible. So when we raise this to the power this one, we have a power r equal to a power n minus qm. A power r, this is taken to the other side, so you have this. So this is a power n into a power m raised to minus q. So this is e and this is also e. So you have a power r to be e with r less than m. But here we have stated that m is the least positive integer, for which a power m is the identity element. So here r is a number which is less than the least positive integer. So that contradicts the fact that m is the least positive integer. So we conclude that r is 0, and therefore in this we have n to be q into m. So that in turn gives m divides n. So this crudely should be remembered as least divides any other. Now in result 2, we consider G to be a finite abelian group and AB belonging to G. So we have order of A to be m and order of B to be n. Then there exists x in G such that order of x is LCM of m and n. Now let G be a finite abelian group. So this result is established in the case of finite abelian group. We shall consider two members, say A, B in G, with the order of A. That what is given we have written. Now we shall consider two cases. One is m and n are relatively prime. The other one if they are not relatively prime. So suppose they are relatively prime, then GCD of these two is 1. Now we shall denote the least common multiple of m and n to be this. And we also know that whenever we are given two numbers m and n, the product is nothing but the product of LCM of them and GCD of them. And here the GCD of m and n being 1, we must have LCM of mn to be just the product mn. Now consider the element AB. So that we are going to name as say some x. And for this element we must have an order. We shall take that to be k. So let k be the least positive integer such that x bar k is identity element. So x is taken as AB. So AB raised to k is E. Now we will consider x raised to LCM of mn. X is taken as AB. So AB raised to LCM of mn. But LCM of mn is m into n here. So you have mn. Now because G is finite abelian group, you can bring this index inside. So a raised to mn, b raised to mn you have. Here a power m is E, so this one becomes E, and here b power n is E, so you have E. So the product gives me the identity element. So this is k is the least positive integer, this is any other integer. So as least must divide any other, we must have this k dividing LCM of mn. So we shall name this as statement A. Now we'll consider E, which you rewrite in this way, and you know that AB raised to k is E, so you replace this E by this. So then, because again G is a finite abelian group, you can it's an abelian group, so you make use of that. A raised to kn, b raised to kn, and you have b power n, order of b is n, so this becomes E, so you have a raised to kn. So for A, which is the order, m is the order of the element A, and kn is any other element for which a per kn is E. M being least must divide any other, so m divides kn, and because m and n are relatively prime, this should imply that m divides k. So similarly we can establish that n divides k. Now if m divides k and n divides k and mn are relatively prime, then the product should divide k. And here is the proof for that. M and n are relatively prime means you can find two more integers t and n such that mt plus sn equals 1. So you multiply throughout by k, this is what you get, and k being divisible by m as well as n. Here we make use of the fact that n divides k, so you get some mu times n, and here we make use of the fact that m divides k, so you have that to be integer times m. So this is equal to k, and you can take mn out, so what remains is only this. So from this it's very obvious that mn divides k, but k is nothing but order of x. So LCM of mn is LCM of mn, so you have mn being replaced by this, so LCM of mn divides order of x. So from these two we conclude that order of x to be equal to LCM of mn. So that is our claim. So this is established when m and n are relatively prime. Now comes the general case where you have these two are not relatively prime. So in that case, first we consider the prime factorization by the fundamental theorem on arithmetic. You can write m as the product of prime powers, and similarly n is written in this way. Now alpha i's and beta i's are non-zero integers. They could be 0 also. So in this case, for example, if we consider this, here we don't have 11 power 0, so that zeros are allowed. Now we define m prime to be the product of these one with alpha I greater than or equal to beta I. My I range in this way, alpha I greater than or equal to beta I, and n prime in this way. Beta I is strictly greater than alpha I. So for example, see, to understand the meaning of this, we shall consider m to be, say suppose I have this number and n to be this number. Then what do I mean by m prime is this. M prime is 2 cube into 3 square, and n prime is 5 cube into 11. See here, alpha I greater than or equal to beta I have. See, if I consider here, 2 is not present, to 2 power 0 that I'll have, 2 power 0 that I'll have, and here 2 cube I have. So my 3 is greater than 0. When my 3 is greater than 0, where I should put my this number, I should put it in m prime. And you consider 3 square here I have, and here also I have 3 square. So when the powers are equal, then also it should be put in m prime only. Now coming to 5 is present here, 5 is present here with index 1, and 5 cube is present here. So here the index is greater than the index present here. So in such case it should go over n prime. So what we do, we put this one over here. So m prime is taken in this way and n prime. And coming to 11, here we don't have 11. 11 power 0 and 0 is less than 1. 0 is less than 1. So in that case it should be put in n prime. So we have the meaning of m prime and n prime to be this. Now this obviously gives me m prime dividing m and n prime dividing n. So we have these two, and very obviously these two are relatively prime. So which means that the product m prime n prime, the GCD being 1, we have LCM of m prime n prime to be the product m prime n prime. Now we consider the element. Now we introduce another element a prime, which is a raised to m by m prime. We shall claim that order of a prime to be m prime. Order of a prime is m prime, so for which we shall take k to be the order of this element a prime. Now being ordered, it is the least positive integer. All these things are true. So we shall consider e, which is a prime raised to k, and a prime is nothing but m by m prime. So this is rewritten as a raised to mk by m prime. Now this is any other integer, and m is the least positive integer. So you have least must dividing any other. So we have m dividing mk by m prime. So that in turn implies that m prime divides k. That's very obvious. And a prime per m prime, when we consider, we have that to be a raised to m by m prime per m prime, and that is a per m. Order of a being m, we have this to be e. And here for a prime, k is assumed to be the order. For a prime, k is assumed to be the order of that a prime. So least is k, any other is m prime. So least must divide any other. So you have this. So from this m prime divides k, from here k divides m prime. These two together gives us, both of them are positive integers. So you have k to be equal to m prime. So that proves the claim that order of a prime is m prime, because k you assumed and that k you proved to be m prime. So you have this. So similarly we can establish that order of b prime is n prime, where b prime is nothing but, here we assumed for a prime a raised to m by m prime. Here b prime is b raised to n by n prime. So thus the orders of elements a prime and m prime are m prime and n prime, and they are relatively prime. So by the previous case, we must have a prime b prime to be of order m prime n prime, which is nothing but LCM of m prime n prime. So in this case, in the general case also, we have the result to be true. So we conclude that whenever we have, so this is the statement, whenever G to be finite abelian group with A of order m, B of order n, then we can always find an element x in G such that order of x is LCM of mn. So we make use of this to prove result 3, which states that if n is the maximal order element, A is an element whose maximal order is n, and all these are happening in a finite abelian group, and B is of order m, then which means that B power m is e, then the relation between this m and this n is m must divide n. And not only that, b raised to n, b raised to m is e, we know, b raised to n will be e, just because of this it can happen. Now we shall take A to be an element of G of maximal order n, and let B be an element in G with order of b m. Now we'll take D to be the GCD of these two numbers, D to be the GCD of n and m. So by the definition of GCD, D must divide n and D must divide m. Now by result 2, we can find an element x in G whose order is LCM of mn, but we know that LCM of mn into GCD of mn is the product mn, and as we have taken D to be GCD of nm, this LCM of mn should be written as nm by D. Now since n is the maximum order of an element in G, this being the maximum order, we have n to be the maximum order of an element. So what we can say about this n by D? It can either take the value 1 or it should be less than 1. So now since D divides M from here, D divides M by D should be greater than or equal to 1. So here M by D less than or equal to 1 and here M by D greater than or equal to 1. So clubbing these two, we get M by D to be equal to 1. So that in turn gives D to be equal to M. And as D divides N, replacing D by M, we have M dividing N. And from here it's very obvious that N being multiple of M and B power M being M, we conclude that B power N is identity element. So this result says that order of any element divides maximal order of an element. So these are the prerequisites to prove the finite abelian, fundamental theorem on finite abelian.